Right. So today we'll start with the next topic. Now, what we have discussed in fluid flow models is the explicit method. Okay. Now, before we move to discussing an implicit method, I'll want to talk about one issue that is typically faced uh, with the techniques that we have discussed till now, particularly with the choice of methods that we want to use in conjunction with the choice of grid that we have. Okay. So this will then we have to be addressed. Otherwise, we can end up with a solution which is not, which can be quite wrong. So let's look at the equation that we are solving. So the momentum equation, let's say the x momentum equation. There's no source term as of now. So this is the equation that we are solving. That's the x momentum equation. Now when we use the finite volume method to solve it, and then what we get, especially in the pressure terms here, is we get a surface integral, because you multiply it by the volume element and then you integrate over a control volume. So what you end up getting is P on the face times the x component of d gamma. That's the general form of the Gauss's theorem. That's what when we apply, this is what we get. And this is the reason when for the control volume that we are considering, let's say this one. So this was the center node, then we had the east node, the west node, the north and the south. So when you integrate this, then the integral can be written as sum over the four faces, and then the contribution from the sum only comes from the east face and the west face, because for the north and south faces the x component of the area is 0, because the area is pointing in the y direction, so the x component of the area is 0. Right? So for this case it comes out to be pressure on the east face minus pressure on the west face multiplied by the area, which is delta y. Right. So this is exactly what we had done earlier. So I'm just recapping it for you. It's been some time. And this is basically telling us about the pressure force on the control volume. If you think about it from a mechanistic point of view, the way you derived it in the first place was that this is the effect of pressure gradient. So this is the net pressure difference on the control volume. Right? So if the pressure difference is 0, for example, then that means there is no force because of pressure. If the pressure on both sides is 0, on both faces is 0, is equal, then the pressure difference will be 0. So P east minus P west on the faces will be 0, and then you have no effect of pressure. So that means that there is no pressure force in this control volume. The driving force could be something else. Now we also did one more thing to discretize, that was to write the values of pressure on the faces in terms of pressure on the nodal values. So the next step was, so pressure on the eastern face was written as pressure on the eastern node plus pressure on the P node minus 2 And then we had for the western face, we wrote pressure on the P node plus pressure on the western node divided by 2. So that was a linear interpolation that we did. To get the facial values, we took the nodal values and did a linear interpolation. So this is a center average. So what does this come out to be? The P at the pth node gets cancelled. So we are only left with pressure on the east minus pressure on the west divided by 2. So this is where our discussion starts. Yes.
And this P plus PV by 2 leads to error because we are assuming pressure is as linear.
Well, that depends. I mean, the error could come if your grid was very coarse. Okay, so linear interpolation, you know that any function can be approximated with a linear curve if the region that you're considering is small. You can prove that in mechanics. We can easily prove that any curve under a very small dx can be approximated as a linear continuous curve. But so if your grid is very coarse and the pressure is showing some different behavior, then linear interpolation could have errors. Yes.
So how we can define that what should be the minimum size of it for this?
Well, there is no thumb rule that what is the minimum size of grid. So the only thing is that if you want a better, you use linear interpolation, and then you can. There are many constraints, right? So one is your computational power that you want to spend on it. So there is no number that you reach that number and then beyond that you start getting accurate results. So for this we do something called a grid independent study. So you keep refining the grid, and for finer and finer grids you see the solution, and then you see that is it converging beyond a certain point. But that's a property of the problem. That's not a general guideline that can be used. So this is where the discussion starts now. So now what we see is to get the value of the velocity, because ultimately this equation was being solved to get the velocity at the pth node, right? That is what we did, right? So we said that when you discretize the velocity parts, you say that the velocity at the pth node. So when you do del u by del t is written as u at pth node at time n plus 1 minus u at pth node at time n divided by delta t. So we're talking about the velocity at the pth node, and that's being affected by the pressures at the eastern node and the pressures at the western node. So I'll write some comments here, then we'll discuss them. Right. So what we note here is that the velocity on the pth node is being affected by pressure difference on adjacent nodes, not on the sorry, it's affected by the pressure difference on the alternate nodes. So pressure on the eastern node minus the pressure on the western node. So the pressure on the pth node was not a part of it. So in a sense, what's happening is that you have some pressure distribution, but a slightly coarser pressure field is being utilized. The same idea that if you want to take the difference between the pressure, you take difference between alternate nodes, then some information of the change in pressure is lost. If you want to estimate the derivative, it's better to take the derivative difference between adjacent points. That's closer information. So what can happen is that you can it can result in lower accuracy. So if our so this is this effect that we are getting is a property of the choice of our grid in conjunction with the choice of our methods, discretization methods, right? So pressure forms a coarser grid. Pressure in the form of from a coarser grid is used in the velocity equation that may result in lower accuracy. So that's one issue. But there is another bigger issue here, and that is that this method that we are using with this grid can actually result in a very wavy pressure field that we get, or a zigzag pressure field, so to say. I'll give you an example, and then we can understand better from there. So let's think of a situation where there actually is no pressure force. So the pressure is the way we can have no pressure force is when the pressure is uniform. It's homogeneous. So if the pressure is homogeneous, what that means is that the pressure difference will be zero. So if it's the same everywhere, then pressure difference is zero, so there's no net pressure force. Let's think of that kind of a situation. And we are trying to solve for, we are expecting to get a pressure which is uniform. But our method may end up giving something different. I'm just taking the numbers from the book. So let's say you get 100 at one node, the value. The units are irrelevant just for discussion. And then you get 100 at all the alternate nodes. Similarly, you get 100 here, and so on. So while calculating the velocity, let's say at this point, if this was our pth point, the red crossed one, then the pressure difference it sees is zero. Right? It takes an east and the west node, the difference is zero. Similarly, if I'm calculating the let's say the velocity, let's only talk about x velocity. Y velocity will be adjacent points in the up and north and south. So this is now let's say our distribution had values which look like this. And this, remember, is something that we are getting, the pressure values that we are getting by solving the problem. So let's look at this pink node this time. So what is the pressure force it experiences? This velocity cell. Well, it takes a east and a west node for the pressure. So it takes 300. East node pressure is 300. The west node pressure is 300. The difference is zero. So both of these, all the cells, when we are calculating the x and y velocities, they will experience a zero force. Let's give some more numbers. So this pressure field that we have will, using our methods in the choice of grid, this pressure field can develop. There's nothing stopping this field to develop. And this field, using the equations that we have, will result in a zero net force. But were we expecting this kind of a field? No, we were expecting a field where the pressure values were the same everywhere. Because that will result, realistically, in a situation where there's no pressure force. The del P by del X term is zero because the P is the same in all X directions. Similarly, in Y directions from the momentum equation. So the pressure was expected to be the same everywhere. But this is the pressure that we got. And this also results in the same sort of effect on our momentum equations from the pressure as it was if the pressure was uniform. So our current choice of grid and methods allows this kind of a pressure field to develop for this situation of zero force. Agreed? So this is the problem. So this zigzag pressure field or a wavy pressure field can develop. So this is an example of a pressure field that is felt like a uniform pressure by the equations. This kind of a pressure distribution is also sometimes called a checkerboard pressure distribution or a checkerboard pattern. So if during the solution this kind of a pressure field got generated, and then there is nothing stopping this from being preserved. So this will just stay as it is because you've got a pressure field that satisfies the equations. So you sort of have got the right pressure field. So there is no correction as such in this anymore. Okay. And in fact, if you, this was a very special case of no pressure force. But let's say you have a pressure which is different from this, which is not uniform. So let's say you think of any pressure distribution that is not uniform. And then I add this to it. That is very much a solution. You take any solution, you add this to it, and that is because the difference will again, this 100 minus 100 will get cancelled, right? So if you add a 50 to 100 and then a 60 to another 100, difference still is 10. Okay, so I can superpose this kind of a checkerboard pattern on any pressure distribution which is non-uniform. That is also a solution. Okay, so our current methods with the choice of grid, they have a problem. This can very much develop. So this was for pressure. Let's look at velocity now. So let's look at the continuity equation. So continuity equation is divergence of velocity equal to 0, or in two dimensions del u by del x plus del v by del y equal to 0. So although we don't solve the continuity equation as such, we solve it indirectly by converting it to a pressure equation. But let's say that we were solving it, because ultimately we are indirectly solving it anyways for velocity. So if you solve it using finite volume, then this is integrated over a control volume, and then this becomes u on the face dotted with the well, delta gamma vector on the face, and this is summed over all the four faces, right? That's what finite volume will give us. So we apply the Gauss divergence theorem first, convert this volume integral to area integral, and then we convert that area integral to a sum over four faces. So this I've just done it in one step. So let's expand this. So on the eastern face, we have, the area is in the x direction. So we get the x component of velocity. So that's u on the eastern face. And what is the area? Area is delta y. So I'll get u east minus u west times delta y. And then for the north and south terms, we'll get v north minus v south times delta x. Alright? Now let's look at only this term for now. Now u east will be written in terms of nodal values. So there'll be u on the eastern face plus u on the pth face by 2. That is how you can use linear interpolation again for finding the eastern facial values. And you can see that we'll get where we are getting at here. Very similar. Now again, what's happening is that the in this velocity equation, it's the alternate nodes talking to each other. So here, what we want is it's so thanks. So again, we see that the alternate nodes are talking to each other. Okay, so in the grid that you have, it's this and this, for example, talking to each other. So we get again velocity from a coarser mesh that is being used in the continuity equation rather than the velocity at the adjacent nodes. Alright. And since this equation actually becomes an equation for pressure, so what happens is the pressure at the pth node depends on the velocity at the east and the west node. And earlier we saw that the velocity at the pth node depends on the pressure at the east and the west node. So this checkerboarding that we are getting can result in solutions which are erroneous. So does everyone appreciate the problem that we have? So here also the velocity, if let's say the x velocity we're talking about, if the x velocity looked like it was 100 here, 100 here, but 400 here, that would also very much have be valid in the sense that this satisfies continuity. The way we are using it, implementing it, because u on the eastern face 100 minus 100 divide by 2 is 0. Similarly, if you have a 400, then after this, so 400 minus 400 divided by 2 is 0. But this is not a uniform. This velocity profile that we are getting is not what we expect. We expect the velocity to be same everywhere. Now again, this only happens if you have a 1D problem, because in 1D you have du by dx equal to 0. But here you also have this, plus this term, that should be 0. So my discussion of this being 0, the difference, is only valid for a 1D case, where du by dx is equal to 0. But here, this difference plus the difference in the y velocity, which is alternate nodes, has to be 0. But the point is that there is no communication between the alternate points. So completely different field values can develop, resulting in the same effect. So the question is, how should this problem be addressed? So one solution is to use a grid which is called staggered grid. So I'll show you what this looks like. So let's draw the mesh that we have. So let's say this was the mesh that we have, and earlier we were calculating. We have these control volumes. So earlier we were using these as the nodes. So this was, let's say, pth node, then we had the east, the west, and so on. So now what we'll do is, we will have different control volumes for different fields. Earlier, the same control volume was used for all three fields, u, v, and p. So you're calculating the u at the center of the control volume was capital P, and the same for v, the same for p. But now what we'll do is, we'll have different control volumes. So we'll have the pressure control volume will still look like this. So this is going to be the pressure center. So the control volume for pressure is this. So this is the pressure control volume. But for velocity, for x velocity, for example, the x velocity will be defined here. So this point will be the u center. Similarly, to get a control volume for u, the control volume for u will look like this. It's staggered. So the control volumes for pressure and velocities are staggered. So it's just like, you just move the control volume for velocity to the right. For y velocity, so this is the v control volume, and the v is defined at this point. So this is the v center. So if I just zoom into it, so this was our previous control volume, but now we have the control volumes which look like this, and another one which looks like this. So the pressure is defined at this point, and this is the pressure control volume. The velocity is defined at x velocity is defined at this point. So this is the x velocity control volume, and the y velocity is defined at this point. So this is the y. So for naming convention, we are still using the same, in the sense that this is P, this is our eastern face, this was our northern face, capital E node was here, capital N node was here. So now we'll use the words mesh and a grid. So mesh will denote the actual mesh that you had formed from your geometry, where in here the black one is the mesh. But for finding for the control volumes discussion, we'll call them grid. So the grid for u velocity, the grid for v velocity are different from the mesh grid that you have. And the grid for P, that is the pressure, is the same as the mesh. Clear? So u velocities are defined at the center of x faces. So this is called a staggered grid. This is different from the grid that we had earlier, which was called a co-located grid. So co-located, everything is located at the same cell. So pressure, u velocity, v velocity, all in the same cell. That's co-located, and what we have we are discussing here is called staggered grid. So what we'll see is that with the use of this staggered grid, it will avoid the pressure and velocity decoupling problem that we were getting earlier. And that is the reason we have proposed this grid, to avoid this pressure and velocity decoupling. So we'll be using the staggered grid for our discussion for the implicit methods that we'll be discussing now onwards. Just to give you a practice in the use of these grids as well. Okay. So let's let's see how this kind of a grid avoids decoupling. So let's first see how let's look at the first equation, the u momentum equation. So in the u momentum equation, now the u momentum equation is not being solved on the nominal cell, it's being solved on the control volume for u velocity, right? So which was denoted with the green color. So this is our, so the u velocity is defined on the eastern face this time. So if you're this is the control volume, and then you're trying to write the pressure difference, Now, what happens is you need, when you do the discretization, you will need the pressure here minus the pressure here, because you were getting the pressure on the faces, right? But interestingly, the pressure at the eastern face of the U grid is actually capital E, and this is P. So in the U momentum equation, you end up using pressure at the eastern face minus pressure at the pth face divided by 2. So now what's happening is that the adjacent nodes are talking to each other. With the choice of this grid, we don't have to go to alternate nodes. Clear? So this is how it is going to avoid these decoupling or the checkerboarding pressure that we could get, and that could be a valid solution to the problem using the methods that we are using in co-located grids. But in staggered grids, when we get the pressure terms on the boundaries, the boundary of the U grid is actually coinciding with the eastern and the pth nodal points, where the pressure is defined. So this is the benefit of defining pressure and velocity at different points. Now, similarly, when you are doing the continuity equation is solved over the nominal cell, which is this one. So here you need the velocities on the eastern face and the western face. But now with the current choice of grid, U is actually defined on the eastern and the western faces of this nominal cell, right? It's already available there. You don't have to do any interpolation. For indexing, when we'll be using it in the next class, indexing wise, it becomes a bit confusing sometimes. So the indexing wise, we'll call this as I comma j. So the boundary will then have coordinates I plus half comma j, and this will be I minus half comma j. So your P, the pressure, will be defined on I comma j, whereas your U velocity, for example, will be defined on I plus half comma j and I minus half comma j. Alright. So when we write the equation, predictor equation, we'll be writing it for not ui comma j, we'll be writing that for ui plus half comma j. So that is the actual problem with staggered grid, that when you're dealing with complex meshes, it becomes very confusing how to use it. For simple situations, it's easy, but life is not as simple as this one. So this was proposed many years ago to solve this pressure velocity decoupling problem. But when we got better machines available to solve problems, we realized that we are solving very complex problems with complex boundaries and geometries. And this choice of staggered grid actually became a hindrance to solving problems comfortably. So then we came back to co-located. Nowadays we end up using co-located grids. So I had all this discussion with you because I would want you to know this, because this discussion will come up if you work with CFD. But most of the solvers nowadays are using co-located grids again. But now what we have done is the choice of grid is still the same, but we have modified our methods. Ultimately, what we were doing was to get the value on the faces. We are using the linear interpolation method. If you use some other kind of interpolation that allows communication between alternate points, that is also valid. Ultimately, we want to avoid the alternate discussions. We want to have adjacent discussions. So if we have a method that allows adjacent points to communicate, that's good enough. So we use all kinds of least squares methods and so on that you can learn in an advanced course in CFD. But for now, the idea to take away is that staggered grid allows to avoid this, but since we would want to have some practice of using a staggered grid, so the implicit methods that we'll propose will be discussed in light of staggered grids. But they can very well be applied to collocated grids as well with the same idea. The implicit ideas are not different. It's just that we are getting some practice in using this staggering, because staggering is a bit more complex than collocated grids when working out the equations. Right. So thank you, and I'll see you on Thursday.